Everybody, it is my pleasure to present this research today. My name is Sadra Majidzamani and I'm a bachelor's student from the Department of Orthotics and Prosthetics at the University of Social Welfare and Rehabilitation Sciences in Tehran, Iran. The title of our research is the use of virtual reality for training individuals with upper and lower limb prosthetics, and I intend to present to you my literature review on this topic. Here is an overview of my presentation. We will start with the objective and introduction to set the context for our work. Then I will detail the materials and methods used in our study. Following that, we will explore the key findings derived from our literature review. Afterwards, we will move to discussion of these findings and finally present our conclusion and relevant references. Our main research focus is on enhancing prosthetic rehabilitation through the application of virtual reality. The primary goal of this research is to review studies that introduce and evaluate the effectiveness of VR systems in improving the rehabilitation of patients with upper and lower limb prosthetics. Specifically, we aim to understand the role of sensory feedback mechanisms based on VR, such as audio-visual integration and augmented reality. This focus helps us see how these technologies improve motor function learning, enhance control during object grasping, and improve walking performance in prosthesis users. Additionally, this study also explores the potential integration of VR technology with more advanced approaches, including game-based rehabilitation and the control of myoelectric prosthesis. Now moving to the introduction of our topic, virtual reality or VR has a rapidly growing role as an innovative and transformative tool in the field of rehabilitation. Its application has expanded significantly, particularly for training individuals who use prostheses. VR offers several key advantages. Advances in this technology have enabled the creation of immersive environments where patients can experience real-life scenarios in a controlled setting. Ultimately, this helps patients achieve a suitable level of control over their prosthesis. VR-based training systems provide a promising approach for enhancing the training and skill levels of both upper and lower limb prosthesis users. Continuing with the benefits of VR systems, they offer unique advantages that are crucial for effective training. These include the simulation of desired real-world conditions, providing a realistic training ground. Furthermore, these systems have the ability to provide real-time feedback, which is essential for immediate learning and correction. Lastly, they have the capability to create customizable training modules which can be tailored to the specific needs of each patient, making the rehabilitation highly personalized. In addition to these features, the use of similar technologies such as augmented reality or AR and mixed reality or MR further enhances these capabilities and significantly improves training conditions. Now let's move into the materials and methods section of our study. Here I will explain the systematic approach we took to conduct our research and identify relevant literature. For our study, we conducted comprehensive searches across several key academic databases such as PubMed, Scopus, ScienceDirect, and Google Scholar. We utilized a range of important keywords to ensure a thorough and relevant search. These included virtual reality, augmented reality, mixed reality, prosthetic control, sensory feedback, grasp control, embodiment, prosthesis training, and myoelectric prosthesis. Our search period covered studies published from 2005 to 2024. From the extensive results of these searches, a total of 16 articles were carefully selected and thoroughly reviewed for our analysis. Next, we will discuss the main findings derived from our review of the selected articles. The articles used in this study were categorized into three main groups based on their focus. 8 of the reviewed studies focused on training and control of upper limb prosthetics in individuals with limb loss, especially concerning augmented reality-based feedback and motor learning. 6 studies concentrated on training individuals with lower limb prosthetics, emphasizing improvements in walking performance and the use of VR with auditory feedback systems. And lastly, 2 studies examined the use of new technologies like VR for both upper and lower limb prosthetic training and general feedback mechanisms. A selection of patients with both upper and lower limb prosthetics participated in these studies, utilizing various VR systems. These included commercially available systems like Oculus Quest 2 and HoloLens 2, as well as specialized platforms like the Computer Assisted Rehabilitation Environment or CAREN. In some studies, the training sessions were specifically designed to integrate visual, auditory, and sensory feedback to enhance overall motor function performance. For individuals using upper limb prosthetics, a significant challenge is faced in object grasp control, primarily due to a lack of sensory feedback from the prosthesis. This often leads to practical difficulties such as accidentally dropping or crushing objects during daily activities. Augmented reality or AR systems like the one developed with Microsoft HoloLens show significant potential in addressing these issues by providing crucial real-time feedback. In one innovative AR-based system, for example, grip strength feedback was reported with different colors directly during the grasping action. Experiments such as asking patients to pick up an egg demonstrated that this system significantly improved users' ability to handle fragile objects without breaking them. However, it was observed that improvements varied across different tests, indicating that AR feedback systems might require customization for optimal performance across various motor skills. Furthermore, studies have shown that prolonged and consistent use of AR systems over time significantly enhances users' motor control. Beyond AR, another innovative training system developed based on VR technology is the virtual prosthesis emulator known as Viper. This system is specifically designed for individuals with myoelectric prosthesis. The Viper system focuses on enhancing myoelectric prosthetic control by incorporating mechanotactile feedback, which provides physical sensations to the user. A key advantage of this system is that it allows users to adjust settings at any given moment to achieve their desired outcome, offering a high degree of personalization. The image on this slide provides an example of a prosthesis simulator that incorporates a pattern recognition system similar to those used in advanced VR training. Individuals with lower limb prosthetics also face significant challenges, notably in maintaining balance and achieving symmetrical gait patterns. To address these issues, several studies explored training with treadmill-based VR systems that utilized specific auditory cues. The aim was to improve gait performance and balance. Users who trained with simultaneous auditory feedback showed good and consistent improvement across various walking-related parameters, including stride length, step length, and the time required to take a step. For transfemoral amputees in particular, a slow-paced auditory cues during walking proved beneficial, allowing them to maintain better control over their prosthesis. Over time, the consistent use of this VR system led to the development of more balanced and natural gait patterns. The image here illustrates an example of a walking simulation within a VR prosthetic system setup. Complementing these VR treadmill systems, advanced platforms like the Computer Assisted Rehabilitation Environment or CAREN are widely used for training. The CAREN system excels at simulating complex real-world conditions for patients, which further contributes to significant advancements in gait improvement. The image on this slide shows the immersive environment of the CAREN system. Collectively, these findings strongly highlight the considerable potential for widespread adoption of VR-based training systems specifically tailored for lower limb prosthesis users. Now let's move on to the discussion section of our findings where we will interpret the implications of the reviewed studies. Here are the key discussion points derived from our analysis. Firstly, regarding VR effectiveness, the study results clearly indicate that VR-based training systems, especially when integrated with crucial sensory feedback like audio and augmented reality, significantly enhance rehabilitation outcomes for patients. However, we also observe that despite considerable advancements in the development of sophisticated upper limb prosthetics and VR-based training methods, challenges remain. Particularly, difficulties persist in the rehabilitation process concerning training users to adapt to daily activities with their prosthesis. Conversely, for lower limb prosthetics, the potential is very high. Among individuals trained with VR systems integrated with auditory cues, various walking-related parameters have significantly improved, clearly demonstrating the high potential of these new methods for clinical use. Finally, looking to the future, our research suggests that to further enhance users' functional levels, future research should strategically focus on optimizing these existing systems. Furthermore, exploring the integration of multimodal feedback combining various sensory inputs will be crucial. To conclude our presentation, I will summarize the main takeaways and the overarching message of our study. In conclusion, our study strongly affirms VR's significant impact on rehabilitation, specifically VR-based training when combined with essential sensory feedback such as audio and augmented reality clearly enhances patient rehabilitation outcomes. Secondly, we identify substantial clinical potential. New VR methods show high clinical promise, particularly for improving walking performance and functional independence in individuals using lower limb prosthetics. This slide presents the key references that were reviewed and utilized in our research. And finally, thank you very much for your time and attention.